So the recording is on now. Today's lecture is, I think, probably one of the most useful in this entire lecture course. And I've said this a couple of times. I also personally find it very, very interesting. And I hope you will as well. There are a few nice little experiments that we're going to be doing throughout this course, throughout this lecture. But this lecture is all about the second half of our discussion on posterior analyses. So what we finished with last week was a discussion of how you go about summarizing posterior information. And we said that if we have some posterior distribution, some posterior function that we want to use to make some inference about a parameter theta, then in many regards, the posterior itself is the entire description, the entire inference about theta. However, we said that often, people don't think in terms of entire distributions. They like to have numbers that they can summarize distributions with. And so that generally led us to the concept of summarizing posterior distributions using things like point estimates. And we spoke about how you can define a whole range of different point estimates. So you can define, for example, you can describe your posterior by the posterior mean, which is saying that I want to take the point that minimizes quadratic loss between my point estimate A and my parameter, my true parameter PDF theta. We said that you could also you could take the median of the posterior. That would give you, that's essentially minimizing the absolute error loss. You could use the mode, the maximum value of the posterior, and that's minimizing the 1, 0, 0, 1. So we spoke about point estimates, and we also spoke about how having a particular single value of a parameter is also not necessarily the best way in which you want to describe your parameter inference. You want not necessarily the thing you want for your inference, because generally you want to know what is the range of values that my parameter of interest might be able to have. And that then led us to the concept of credibility intervals, which are essentially giving us a region over which a parameter is probabilistically likely to reside. And we can do that in the posterior because we have this full Bayesian framework, this full random variable framework where all parameters are essentially random variables. So that's where we ended last week, talking about credibility intervals and things like that. What we're going to talk about today is not taking a single not taking a single value as the description of our posterior, but rather is about how we can go about using an entire distribution of samples from a posterior or that describe our parameter in order to perform our inference. But before we get to actually creating posterior realizations, there's one point that is related to creating realizations that I think is worth commenting on, worth discussing. And so that's what we call predictive distributions. So throughout the course so far, we've focused pretty heavily on estimating the value of a parameter. So we have some parameter theta, we have some data x, and we want to estimate the true value of theta. But generally, or in many applications, what we're actually interested in is not knowing the value of theta specifically, but rather in being able to make some sort of a prediction about what's going to happen if we take future data. And that prediction is one of the widely formed types of inference. It's one of the main ways, one of the main mechanisms of doing inference that we discussed a few lectures ago. And so what we can do is within our Bayesian framework that we've been discussing, we can actually utilize the models and the parameter estimates that we make via the posterior distribution to create predicted values of the data should we take more data in the future. So when you're making a prediction, though, there's a couple of sources of uncertainty that are important, because predicting the future is difficult, and it's difficult because of two main sources of uncertainty. The first is the uncertainty on the parameter values that you're using as your predictive generative function when forecasting into the future. So the parameters that you've estimated, if they are not the truth, then they will bias your future guess, your future prediction. So that's the first type of uncertainty. The second type of uncertainty is driven by the fact that any future value that you measure for a parameter is itself a random event. So you can have a prediction, right? So if you were to take, I mean, the easiest example of this is to think of a linear extrapolation. Let's say that you had some time series, and it shouldn't be surprising to everyone that it took me 2 slides before I wanted to find my notepad, which I don't have access to today. So I'm going to flip over to the whiteboard and we'll have a little draw on that. So if you imagine a circumstance where you have a time series of some data. So this is like a time on the x-axis and some value of a parameter on the y-axis, just call it y. And there's some distribution of data in this region. So let's just draw a cloud of data that looks something like that. Now, if we wanted to make a prediction about the future values that t could take, we might just do a simple regression or linear fit, where we essentially fit a model to this distribution, and we then say that at time t future, the value that I expect t to have is going to be, say, this one here, right? But the next observation that I actually make at a time t is out here, call it, t1. Pardon my handwriting on a trackpad. The value that we would actually measure there is itself a random event. So it will have some scatter, some uncertainty, and that random event might actually sit here, even if the extrapolation is perfect. If the information in that extrapolation is perfect, the actual observation that we make need not be what's on the line because it's a random draw. Hopefully that makes sense. So going back now to our lecture slides. In classical statistics, the standard practice is what I just showed you, is to make some prediction based on the assumption that the existing data are a perfect realization of, give you a perfect inference about the underlying true model, and then to extrapolate that model and then to incorporate some uncertainty around it. Yeah. That is essentially saying it only incorporates this second type of uncertainty. It doesn't incorporate the uncertainty that the parameters that we've estimated need not be the correct ones. They have themselves some uncertainty. And so that leads to inference, or rather predictions about the future that are overly precise. They are more precise in the prediction, or they believe they are more precise in the prediction than they truly should be. The distribution of predicted values has too small a scatter than what it should, because it fails to take into account this primary first source of uncertainty. Fortunately, though, as you're all well aware, given our discussions on Bayes' theorem, Bayesian statistics, Bayesian inference doesn't have this limitation, because we know, and in fact, the whole framework is based around the fact that the parameters in our model are themselves random draws. They aren't the truth. They are random draws from the underlying distribution that contains the truth. And so what we can do is we have some series of past observations, xi to xn, and those variables are some, and those are some drawn from some density function, which has some likelihood p of x given theta. We have some prior, which we already know about given last week's lecture, and we can combine the prior and the likelihood to give us some posterior. Now that posterior, we've discussed somewhat at length. What we're going to talk about now is how we can take that posterior and we can generate what's called the predictive density function, the predictive distribution function of new data y given observed data x. And the way in which we do this is we go via the posterior p of theta given x. Now that posterior function is nothing different to what we've seen before. And now we have a second term here, which is the likelihood of the new observations y given the model of given the parameter estimate theta. So it's the integral of the likelihood of a single point y times the posterior, which we've measured p of theta given x. This is a pretty simple formula, but it allows us to create predictive distributions of data given an uncertainty on both the actual value of the parameter that we're interested in and the uncertainties inherent to the random future draws of data as well. So let's go back to our standard. Let's go back to our standard distribution here, predicting a coin toss. And we've got a binomial coin toss that has a coin with unknown bias. That bias is given by the parameter theta. And we've drawn some observations x that are drawn from that binomial. So x successes from n trials given a biased coin that is biased by some probability theta. We know from a couple of lectures ago that or rather from last lecture, that the conjugate prior to the binomial distribution is the beta distribution. And we know, again from last lecture, that this gives us the posterior, that the posterior samples are drawn from a beta distribution, which has modified prior parameters based on the number of successes that we saw in the data, here and here. Now, let's suppose that we want to take, or we expect that in the future, we're going to take capital N further observations. And we want Z to be the number of successes from those N future trials. So Z, the likelihood of Z given the true biasing theta is also a binomial, now capital N instead of lowercase n. And the likelihood is just the binomial likelihood. So nothing new here. But with this likelihood, we can now compute the predictive distribution of Z given the observations that we make, the number of heads that we see in our N trials, and we can do it via the posterior, but we can just directly compute the predictive distribution. So we don't actually need to look at the posterior for the moment. We just want to say, I don't actually care what the bias is on my coin. What I care about is what is the most likely number of heads that I will see if I do another N trials, capital N trials. Now, because of the conjugate analysis, we can actually do this pretty much analytically. So we know what this likelihood is. From the conjugate analysis, we know what the posterior form is. So we can just construct this integral directly. And when you do that, you end up with this. So this is the likelihood of the Z given theta. And this is the posterior here. This is this beta p plus x q of n plus q plus n minus x. That's this thing here. And you can then rearrange this. So this thing on the denominator here is what we call the beta function, not the beta distribution, the beta function. It's just a way of combining those three gamma the gamma functions that sit at the front of the beta distribution. So if you don't know what I'm talking about, have a look back through our distributions, and you'll see that at the front of the beta distribution, there's a collection of gamma functions, gamma A times gamma B divided by gamma A plus B. And that fraction of gamma functions is generally collapsed into a function that's called the beta function, beta of these things. And so we can just pull out that constant out the front. And when we do this integral, we get another beta function. And that beta function is of the same form, but now with parameters z plus p plus q and q plus 2n minus x minus z. So you can do all this yourself. It's literally just a simple rearrangement. And then the integration here comes from the fact that the beta distribution is a probability distribution. And so integrating it from 0 to 1 integrates to unity, given that normalization constant out the front, the beta function, which is where this additional term comes from. So we end up with this thing here, the probability distribution of z given x. So we've put in no actual observations here yet. We've just created the true predictive distribution for an arbitrary bias, for an unknown bias, given a whole series of observations, x, given that unknown bias. And what we can do now is we can take this distribution and we can predict what the future outcomes are likely to be given this predictive distribution. Now, one of the things you might have noticed is that I've picked the biased coin toss, which is a binomial distribution. I've picked the priors to be beta functions because they're the conjugate. And this will be ringing bells to some of you to say, this is exactly the same setup that I had during our first excursion into Bayesian statistics, which was looking at the outcomes of our 3 scenarios at the pub. We had our 3 friends, one of which was a fortune teller, one of which was a wine critic, and one of which was a classical musician. And we're now asking the question, given the posteriors that we generated for those 3 scenarios, what is the most likely outcome? What is the distribution of expected outcomes z for an additional 10 trials? So if we ask them to do the test again, what is the distribution of most likely outcomes? What is the distribution of most likely observations of z, given we've observed 10 successes from 10 trials and we applied the priors that we applied? And what you can see is this distribution here. So my new distribution P of z given x for the fortune teller is now peaking at 5 correct out of 10 trials. So it's very likely, or it's most likely, given this distribution, that they will get it wrong 50% of the time. And you'll remember that that's because my particular prior on that person being actually able to tell the future was very, very low. Conversely, the classical musician now has a much stronger peak in the number in the expectation of getting 10 outcomes. So if we were to take the expectation of these 3 distributions, the arithmetic mean of these 3 distributions, the expectation of the fortune teller is that they'll get 5 right out of 10. The expectation of the wine critic is that they'll get 8 or so out of 10. And the expectation of the fortune teller, of the classical musician, is that they'll get close to 10. And so this is the utility or the benefit or the power of predictive distribution. The last, arguably most important method of interpreting and discussing posteriors is related to our whole discussion that we had about simulating data three or so lectures ago. posterior simulation is, I think it's fair to say that posterior simulation is overwhelmingly the driving factor that has made Bayesian statistics as popular as it is in modern science, in modern empirical sciences like physics and astronomy. Why is that the case? Well, we've seen that there are lots of complex functions that we have, which are combinations of a fairly simple prior and a fairly simple likelihood that result in very, very difficult to integrate integrals of the likelihood, so likelihoods of observing the data on the denominator. This was the denominator of our Bayes theorem was very difficult to integrate, you'll recall from a few lectures ago. What posterior simulation gives us is a mechanism to derive samples from a posterior without having to worry about a lot of the complexities that we get when we have arbitrary combinations of priors and likelihoods. It has the additional benefit of not requiring us to have any sort of analytic expression for the posterior. And it means that we also don't have to limit ourselves to describing the posterior as a single value of say, the point estimate or of the credibility interval. Because if we have n samples that are samples directly from the posterior, then we can do all manner of things with them. We can compute trivially the point estimates. We can compute means, medians, modes. We can compute trivially the credibility intervals. We can compute the quantiles of the distribution. We can make higher order statistics that describe higher order moments of the distribution. We can do all these sorts of things, provided we have some mechanism to reliably generate samples from the posterior. And posterior simulation is that method. It is that mechanism for generating those samples. And overwhelmingly, the most important thing, the most important mechanism for generating posterior samples is the Markov chain Monte Carlo, the MCMC. And we are going to spend the next hour talking about MCMC. This is, I do not think it is an exaggeration to say, this is the thing that you will use most out of this entire lecture course in your academic careers. It is extremely powerful. It is extremely popular, and you'll see why. We're going to go through and we're going to talk about the fundamentals of MCMC. What is MCMC? What is a Markov chain? Why do we do it? We're then going to create our own Markov chain Monte Carlo, or actually two different Markov chain Monte Carlos. And we're going to take you through how you actually generate that in a very step-by-step mechanism. And that allows us to really have hopefully a clear understanding of MCMC. And the goal of this is that I want you all to be able to leave this lecture course with a confidence that you understand MCMC and you can apply MCMC on your own, because that will put you in excellent stead for working within the empirical sciences, because this really is one of the most used things in the empirical sciences. Okay, I think that's enough build-up. Let's get into it, because this is actually quite interesting and I think quite fun. So what MCMC is it's a mechanism for generating samples from a target distribution. One of the things I love about MCMC is, unlike almost everything we've discussed in this course so far, MCMC was created by physicists. It was created by us, and then the statisticians then said, wow, that's really useful, and adapted it for statistics. But this is something that was born of the natural sciences, and this is one of the reasons why it's so widely used, because it is something that was created specifically to solve problems that we deal with in the natural sciences. So it was first introduced to create a mechanism for generating efficient samples of energy levels of atoms in a crystalline lattice. So those of you who are working within the physics faculty, in particular the condensed matter department, will be all too familiar with this problem of generating a good distribution function that gives you the energy states of atoms in an arbitrary lattice given some construction. The way in which MCMC works is as follows. We have some arbitrary target distribution. We call that target distribution pi. And so pi has some distribution of some series of variables x, and those variables x are drawn from some what we call state space or sample space. And that state space is, some n-dimensional thing of real numbers. So it's an arbitrarily high dimension posterior or distribution. We'll not get to the posterior in a minute. Generally speaking, Markov chain Monte Carlo is applied to scenarios when the distribution, the target distribution we're interested in, is sufficiently complex that we can't sample from it directly. Okay, so it doesn't have a conjugate, or it's not a conjugate analysis. It's not something that's in one dimensional that we can use rejection sampling from or inversion sampling. This is a high dimensional problem which has complex distributions that we can't directly sample from. And that's when the Markov chain Monte Carlo comes into its own. The indirect method for generating samples from this distribution is to construct what's called a Markov chain. The Markov chain exists within the state space, within this state space omega, and it has some stationary distribution, which is the name of the underlying distribution that the Markov chain tries to reproduce, which is the target distribution, pi of x. The point of the Markov chain is that if we run it for long enough, then the values that are simulated by the Markov chain actually give us samples from the target distribution. And that gives us a mechanism for generating these samples in the distribution that we want to analyze. I appreciate that paragraph is chock full of jargon. So don't worry if you didn't understand fully what I meant there. We're going to go through this step by step in the course of the next few slides. Okay. So what is a Markov chain? A Markov chain is a sequence of random variables that follow a particular conditional probability. And that particular conditional probability is that the probability of the xt plus 1th observation being value xt plus 1, given that the previous observation was xt, and the one before that was xt minus 1, and the one before that was xt minus 2, all the way through to the first one, which was x0. So the probability of moving to the state t plus 1, given this whole sequence of previous states, is equal to the probability of being at state, I jumped ahead. So the y here is the same as xt plus 1. So the probability of moving to xt plus 1, given this full sequence of occurrences, is exactly the same as the probability of moving to xt plus 1, given that you are currently xt. That is to say, the previous locations the x t minus 1, t minus 2, t minus 3, all the way through to x0 have no influence over the probability of stepping to the next place. The Markov chain describes a sequence of random variables that is memoryless, that has no memory of previous states except for the one that it is at right now. And so the outcome of the next step in the sequence is determined exclusively by the current location, the current place in the state space, xt. That is a Markov chain. The probability for going from xt to xt plus 1, where xt plus 1 can be any of the positions in the state space, is given by something called the transition probability. Okay? So let's formulate this a little bit more. The probability of going from point x is equal to xt somewhere in the state space to point y is equal to xt plus 1 somewhere in the state space, somewhere else in the state space, in n discrete steps. So I want to go from here to here in a finite number of steps. The probability of making that chain of going from one point to the other, from point x to point y in n finite steps, is given by the conditional probability of y given x, which is the summation of the probability of going from x to x1, from x1 to x2, from x2 to x3, x3 to x4, x4 to x5, x5 to x6, all the way through to xn minus 1, and then the probability of going from xn minus 1 to y. Now, you've probably just seen from my little hand gesture, this is every possible series of steps that can take you from point x to point y in n steps. Right? So if n is equal to 3, let's draw a really simple diagram of this. So if n, I'm going to clear this drawing. So let's say that this whiteboard is my state space, and I want to know how rapidly I can go from point x to point y. Now let's make our lives pretty easy. And let's say that this grid of points is fairly small. So let's say that there's a point line there, another line here. So these are the available states in our state space. Okay, so it's just a one-dimensional thing, and we want to know how to get from x to y in, let's say, 1, 2, 3, 4, let's say 5 steps. Okay, so the possible ways that we can go from x to y in 5 steps is 1, well, I'm going to draw arrows. Let's draw 1, 2, 3, well, let's do 6, 4, 5, 6. So let's do n is equal to 6. Okay, so that there is an example of one path that can get you from x to y in 6 steps. Yeah, but you can equally go 1, 2, 3, 1, 2, 3, 4, 5, 6, where I've just looped back after the first step. Or, you know, obviously 1, 2, 3, 4, 5, 6, right? All of these are valid paths that get you from x to y in 6 steps. And when you're doing this calculation that we just had on the slides, we need to integrate, or rather sum over all possible combinations of those things. Okay? So that's what this transition probability calculates. The way in which you can think about this transition probability is that for a finite state space, like what we just showed, it produces an omega by omega matrix. And that matrix has the probability of transitioning from state X to state Y, given you're at state X. Okay? So again, it's just this conditional probability, and all entries of this matrix are probabilities. So they have to be between 0 and 1. And an important thing to recognize is that the rows of P of X of Y have to sum to unity. And that's because if you are at state X, which is each row is one state X, if you're at one state X, the probability of going to X0, X1, X2, X3, all the way through to Xn of all of the available states has to sum to 1. Because if it doesn't, then there's a finite probability that when you reach state X, you disappear from the universe after that step, right? Which obviously can't happen. And so the rows of this thing have to integrate to unity. So let's actually visualize this whole process. I just gave you a very, very bad drawing on a whiteboard. Let's actually do this in a slightly more sensible mechanism. And the way in which we're going to do this is using a very particular type of Markov chain. And that particular type of Markov chain is what we call the random walk. You might be familiar with the random walk. The random walk is a Markov chain where the probability of transitioning from point X to another point in the state space is uniform, and it's uniform to the two adjacent steps only. Okay, so if we are in here, if we are at point, X1, there's a 50% chance we'll go to X0. There's a 50% chance we'll go to X2. If we're at X2, there's a 50% chance we'll go to X1, 50% chance we'll go to X3, et cetera, et cetera, et cetera, et cetera, all the way through to Xn minus 1, the 50% chance of going to Xn, and a 50% chance of Xn minus 2. There's some boundary, I've put a boundary here at X, if you're at X0 and at X1, that forces you to step back towards the center. But in practice, we frequently create a state space that is defined in terms of differences from the current step, which means that these limiting cases never actually happen, because in order to be there, you would have to be at X is equal to X of infinity and X of minus infinity. We'll see what that means in a second. So we can program up this random walk really simply. All it is some given, so we have a single step. Our single step is a function. So if I am at location X, I can take a step, and my step will either be back 1 or forward by 1, and only one step, with equal probability. So I sample a single one of these two numbers with equal probability, and that determines whether I step forward or back, +1, -1. So if I'm at 0 and I run the step, then I end up at -1. If I run 0 and I run the step again, then I end up at 1, right? Because there's a 50% chance of ending up in either way. So question here, do the jumps from state lines in the state space have to be continuous, or can they start on the top of line 1 and continue to the bottom of line 2? So in that first description that I had, I was actually considering a one-dimensional random walk. So the vertical displacement was, meaningless. But that's a really good question, because what we're about to look at is the multi-dimensional random walk. But the probability of going, in a multi-dimensional sense, the probability of stepping from the top corner to the bottom corner is determined by the transition probability. because that bottom corner, so let's say that you had, if this is a two-dimensional state space, then X is actually a vector quantity, X1, X2, and Y is a vector quantity, Y1, Y2. And so all of these then have two values, and then the probability of stepping, so it becomes a three-dimensional cube matrix, an array of dimension 3, and that then describes how you step around the space. But we'll see in a second. That's a really good question. Let's stick with the one-dimensional case, because I think for a second, because I think that this will help visualizing. So the random walk is then just a sequence of these steps. So we pick a particular starting point, which I've just picked as 0, and we then take n random steps, forward, back, back, forward, forward, back, back, forward, back, right, etc., etc. Okay? And so I've just started at some point x, 0. I then take n steps, and I end up with some chain, some Markov chain of random steps. And this is it. This is my random walk. So I start at 0, and I stumble backwards one step, and then stumble forwards a step, forwards another step, backwards a step, backwards a step, backwards a step, etc., etc. All the way, and I walk randomly throughout this space. Okay? I can actually simplify this code, so remove this for loop, because the probability of stepping, as we saw here, is just sampling. Here I sampled one step, but there's no reason I can't sample n steps. They're equally probable. I just need to add a replace equals true here, because I want to be able to draw a 1 and then a 1 again, and then a 1 again, and then a 1 again, and then a -1. But I can simplify the random walk by just having this described as a series of steps. So this will give me n +1s, draws from either +1 or -1. And then my random walk is just the cumulative sum of all of those steps, because that's how we walk. Our walking is a cumulative sum of steps. And so I can do this. I can now create a random walk that is much quicker because it doesn't have this for loop. And I can random walk for, say, 10 to the 5 steps. And what does that look like? Okay, so now I've started out at 0 again, but if I take 10 to the 5 steps, obviously I can walk a lot further than I could if I just took 10. Okay, anyone who's been hiking will appreciate that particular statement. And so what you can see with this random walk is that the random walk sort of hovers around 0 to sort of 50, and then it sort of starts to march off towards positive values. And then they get to around a value of a location of +200. And then the random walk turns around and it marches rapidly away back down to negative values. And then it sort of turns around here again and starts to march back up again. This is one random walk. But that might not be sensible for us. We might want to ask the question, what about if we wanted to run 1,000 random walks? Well, again, we can do that many, many times from the same starting point, and we can generate n random walks. So I've generated now, I've got my function here, n random walks. Oops, 1 second. So I've got my function here, random walk, which I just made faster. And random walk takes a starting point and a number of steps. I can then call this function random walk 30 times, which is what this replicate thing is doing. And this gives me a matrix where every row of the matrix is one random walk. And it generates this. This is a sequence of 30 random walks. And you can see that the density is quite clustered around the starting point early on. And then it gets more and more spread out as the random walks diverge away from their starting value. There's still probably, an over density of points here in the middle, but we have got now some outlying thing. Now, we can use this random walk, this sequence of random walks, to actually explore this transition probability. But rather than actually calculating the probability of stepping between two finite places in the space, given a particular starting point, a particular endpoint, one of the things that's probably a more interesting question is, what is the chance that I return to the starting point? Now, given the name random walk, the obvious sort of context to draw this into is I randomly stumble forwards and backwards in one dimension with equal probability of making a step forward and equal step back. And I want to know, what is the probability of returning home given totally random steps in a finite number of steps? So let's say, I'm going to create a poll here. Let's say, so I'm going to call it just return home, and it's going to have only two options, yes, no. Okay, so in one dimension, given, let's say, what did I say here? The default was 100. In 100 steps, oh no, yeah, 100. So in 100 steps, what do we think the probability in one dimension of returning home is? Do we think that it's greater than, well, let's just ask a simple question. Do you think that you will return home in 100 steps with very, very high probability? Yes or no? So we'll wait until we have a few responses in there. So we have 16 people online, so we'll wait until we have sort of half that as per norm. In terms of the responses, we're at 7. There we go, there's 8. So, okay, so this is interesting. You guys think that the probability of returning home in 100 steps is pretty low. I imagine if I ask that question again, and I ask the question now, so I'm going to clear these results and ask the question again slightly differently. Let's reset results. Okay, now I want to know what the probability, if you think that you will return home in 1,000 steps. Do you think that the probability of you returning home in 1,000 steps is greater than 99%? Do you think you're almost certain to return home if you randomly step for 1,000 steps, forward 1, back 1, forward, 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 back, back, forward, back, 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 etc., etc. Okay, so if we have 1,000 steps, and you can use this as a pretty good guide. Admittedly, you can't really see what's going on down in the business end down here, but that's fine. If you have 1,000 steps, do you think that you'll return home with pretty much certainty? Okay. Now, one more. Good, showing the results. Still no. Okay, interesting. So the answer is, so we can actually compute this. What we can do is we can construct a new function that's called walk home, and walk home runs the random walks from some starting point, x0, and it asks the question, do I at any point return to x0, ignoring the starting point, obviously, because we don't want to, I mean, being home when you leave the house doesn't count as coming home. And if if you do return home after, so if you do return home, then this walk home gives you a value of 1. If you don't return home in the end steps, you get a value of 0. Okay, and then what I do is I run my walk home for 100 steps, so n is equal to 100, and I ask the question, what is the probability or the sum of times that I return home? What is the number of times I return home? So the sum of arrived, divided by the number of walkers, which was 30. And the probability, therefore, of returning home after 100 steps is 93%. So that's actually quite high. It's not certain, which is why the majority of you said no, which I think is the right answer. We can then ask the question though, how does this change as a function of the number of steps? So if I was to take many, many, many more steps, what is the probability of returning home? And so what I can do is I can generate the number of steps as some sequence. So I'm going to generate 20 log equal steps in log space. So starting out with 1 step and then doing, 20, et cetera, then you 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, and all the steps in between. And I just, for that number of steps, run my walk home simulation again, and I compute the probability. And then I plot the probability of returning home given the number of steps. So what's this going to look like? Well, it was 93% at 100. So it's going to be less than that at less than 100. It's probably going to be higher than that, higher than 100 we would expect. And indeed, if you look at this probability, what you find, the probability of returning home if you only take 1 step is obviously 0, because you can't be home, step away from home and be home. So the probability is 0 at 1 step. And then it increases as you go to more and more steps. Now it's a little bit noisy, this curve, but that's fine. It's an empirical measurement we're making here. But you can see that after sort of 1,000 steps, you're very, very close to guaranteed to have walked home at some point in the preceding 1,000 steps. Okay, so if you are a one-dimensional drunk person, you are almost guaranteed to stumble home in 1,000 steps, regardless of whether or not you step forward or backward with random probability or not. If you step for 10,000 steps, then you are, again, basically guaranteed. But what about the case of 2D? What do you think the probability or the guarantee of returning home is in 2D? Now, if I let the step number go to infinity, do you think that there is an absolute certainty that in 2 dimensions, I would find my way home, even if I let my number of steps go to infinity? Oh, missing a T in my text RM. So after a possibly infinite number of steps, will you definitely return home at some point in 2 dimensions, or will you not return home? Do you think that you'll plateau out with some finite probability of returning home, and therefore that there is no guarantee that you will return home? So again, I want you to answer this question. So in 2 dimensions, do you think there is a guarantee that in an infinite number of steps you will find your house again? Or do you think that there is no guarantee that you will, in 2 dimensions, ever find your house again? So 7. Okay, so we have 8 there. So let's move to the next one. So the higher dimensional random walk. So we can take the same function that we had, or roughly a similar function that we had, and generate an n-dimensional random walk pretty trivially. And the way in which we do that is we recognize that steps are steps, no matter whether you're stepping in X, Y, or Z. You're still stepping +1 or -1. It's just now that step has a direction, unlike what it had in the one-dimensional case. And so we just generate the same n steps, exactly like we did previously. The nuance, or the difference, comes by now generating a direction that I am stepping in. Yeah. So what I'm going to do is I'm going to step in for example, the 3 dimensions here is I'm going to sample a value from 1 to 3, and that sample is going to tell me which direction I took a step in. So if I'm working in 3D, that should actually be ND there. So that's a mistake. But if I'm working in 3 dimensions, then this is going to give me a number between 1 and 3. And that's going to tell me that my first step was forward and it was in the X direction. My next step was backwards and it was in the Z direction, et cetera, et cetera, et cetera. So we can then generate our coordinates, which are now 3-dimensional coordinates, X, Y, Z, which is why this has ND columns and N row steps. And we can then just generate our steps. So for each dimension, we step in the relevant places. So if if the first step was in the X direction, then dims here will be 1, X here, I here will be 1, and so this will be true, and therefore the first step will be given to the X direction. That's what this does here. And then as before, we calculate the cumulative distribution of those steps in X, Y, and Z, and then we return our set of coordinates. And so we can use this function to step in multiple dimensions. So let's do a 2-dimensional random walk. So ND is equal to 2, and let's step 100 times. This is what 100 steps in a 2-dimensional random walk looks like. Okay? So this is just 2 different random walks where I've given, well, it's actually 6 different random walks. So I've got 3 in each plot. So where I've given them black, red, and blue, just to show you what happens in 6 random walks with 100 steps. What happens now if I add more steps? So let's now go to 10,000 steps. So this is 6 random walks in 2 dimensions with 10,000 steps. And so now we're starting to see what a 2-dimensional random walk can look like. And we start to ask the question, do we think that given an infinite number of steps, this random walk will ever return to the origin, will ever return to 0 with certainty? So this is the question that we had at the end of last slide. We can add more again. So let's go to 10 to the 5, and we have these 3 random. So you can see that the color here is now becoming a little bit thicker, and where that color is, that's because of the transparency. That's areas where the random walk is stepping over itself again and again and again. And what you can see is like there are some walks which tend to sit around in certain places and then quickly step away and then sit around in another step and another place and all that sort of stuff. But these are the interesting sort of 2D random walks. And they tend to meander. They tend to meander randomly around the plane. And the question is whether or not they actually return to the origin. So we can do it. We can actually construct our walk home function now in ND, just like we had previously. Sorry, in 1D, but now in ND. So instead of having, do we return to X0, it's now, are all coordinates equal to 0? Because that means we're at the origin. We're not at the origin if only X is 0 and the others are not. And in that case, we have walked home. And now we do 10 to the 1 to 10 to the 5 steps. And we generate now 1,000 random walks of each set of steps in each ND. And we calculate our probability and we make our plot. So what is the probability of arriving home in 2 dimensions? Cool. So the majority of you have said that, yes, you think that in an infinite number of steps, you will walk home in 2 dimensions. Before I show you the answers, I want you to answer one more poll for me. I want you to answer exactly the same poll, but now in 3 dimensions. If you have an infinite number of steps, do you think you will find your way home in 3 dimensions? In a random walk where you step randomly in each dimension. So again, we'll wait till this one has a requisite number of people, and then we will continue. Okay, one more. There we go, there's one more. Okay. And I'm going to show the results now. You guys are good. Okay. This is the distribution. This is the probability of returning to the origin given a finite number of steps. This is 10 to the 1, 10 to the 2, all the way through to 10 to the 5. And what you can see is that in 1D, we reach home with absolute certainty after 10 to the 5 steps. In 2D, we're climbing. And it looks like it might be plateauing out, but it also looks like it might continue. And in fact, if you let this play out for many, 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 many more steps, it does actually return to unity. So you are guaranteed to find your way home in 2 dimensions if you step randomly in the random walk. In 3D, however, you're not. In 3D, even with an infinite number of steps, you only have about a 35% chance of finding your way home. And what that means is that, there's a very famous quote from a statistician who worked on random walks that says, who said, a drunk human will always find their way home. However, a drunk bird will not, which is, fairly funny. But, oh, there you go. I said a drunken fish, but they said a drunken bird. So that's the random walk. Why are we talking about random walks? Well, because the random walk is a form of Markov chain, and the Markov chain is obviously a fundamental part of the MCMC. So there's 2 parts of the Markov chain that are important for it to be used in an MCMC and applicable in an MCMC. And that is that it be aperiodic. That is that you're allowed to step back to a location X with 0 lag between the steps. So basically that I don't have to wait a certain number of steps in order to return home. There is a non-finite probability that I will remain where I am. So P of X given X, P of X and X. So the probability that I stay still is greater than 0. So that's an important thing to have, given N is greater than or equal to 1. And that may, if a Markov chain satisfies that condition, or rather, if it has some periodicity that is equal to 1, which means that it can return immediately, then it is said to be aperiodic. If it's bigger than that, then it means that you have to take a finite number of steps before you can return to the location that you're currently at, and that can be bad. The second thing is a concept called irreducibility, and that basically says that I can step to any location in the parameter space given a finite number of steps. So there are no parts of the state space that are off limits to me. And I can always go from X to Y in a finite number of steps, assuming that the probability, the true probability of the target distribution at Y is non-zero. Because if it is 0, then you don't want to go there, so it doesn't matter. Okay, those are 2 important concepts. We can talk about them a bit later because we're running a bit late, and I want to get through this. We're going to now build an MCMC sampler. It's called the Gibbs sampler. And the way in which the Gibbs sampler works is we're going to construct a pair of variables, X and Y, and the joint distribution of those variables is pi of XY. Okay, the way in which the Gibbs sampler proceeds is that we generate a sample from pi of X, so the marginal distribution of pi, in the variable X, and then we sample in turn from the conditional distribution of X given Y and Y given X. Okay, now if we have to know these conditional distributions for the Gibbs sampler to work, and that's a condition that's very important. But let's keep going for a moment. What this does, what the Gibbs sampler does, when you go through this process of simulating from the marginal distribution and then the conditional distributions, this gives us a sequence which is called a Gibbs sequence. And it starts off with some initial values, y prime 0 and x prime 0. And then it gives us a sequence of y1 prime, x1 prime, y2 prime, all the way through to the ends. And even if we choose the initial starting points arbitrarily, we end up with samples that are drawn from the target distribution pi of xy. And the way in which we do this is the iteration proceeds like x of t is sampled from the marginal distribution of pi x given y of t, yt, and the y variable is then drawn from the x variable we just created from this conditional distribution, right? So at each point, you inherit the thing from the last step. So that process is called Gibbs sampling, okay, where you generate a sequence of variables from random draws from a conditional distribution. And this is where the term Markov chain Monte Carlo comes from, okay? So the Markov chain is the thing that we've been speaking about. It's the sequence of numbers whose next value is determined purely by the current state. The Monte Carlo is to do with the Monte Carlo sampling that we spoke about previously, where I'm drawing randomly from a probability distribution. My Monte Carlo simulation is random draws from a probability distribution. So I've generated a Markov chain with Monte Carlo draws. Okay, Markov chain Monte Carlo. So the Gibbs sampler is a form of MCMC. So the way in which it proceeds is we start off with an initial guess in our arbitrarily complex and d-dimensional space. And our guess obviously has to have a value for each of the dimensions. So x, 0, 1 in the first dimension, second dimension, all the way through to the dth dimension. We then simulate a value of x1, in the first dimension from the conditional distribution of x given all of the other dimensions. So the marginal distribution of x. We then simulate the second dimension from the conditional distribution given the margin, the value we just drew, and all of the others. This might not make a lot of sense to you in terms of these formulae. So we're going to just do it, look at it in practice. And so the way in which we can do that is with a simple example. So let's take the bivariate Gaussian. So we have a 2D Gaussian, which has variables y1 and y2, and it has two unknown means, θ1, θ2. It has a known covariance matrix, which governs how tightly correlated the two parameters are, which is governed by this value rho. And we're assigning a uniform prior to the values of theta, okay, to the means. We don't know what the means are, and so we just generate a uniform prior of all possible values of theta, and that gives us a posterior using our conjugate analyses that is drawn from this distribution. Okay, it's a normal distribution where it has mean y1, y2, and sigma or covariance matrix this. We can sample from that directly, but we're not going to. We're going to pretend that we can't. And so we're going to generate the Gibbs sampler. So what we do is we take our conditional distribution of θ1 given θ2 and y. And we know that that is, from our conjugate analysis, that's a normal drawn from this distribution. And then we do the same conditionalization, which again, from our conjugate analysis, we know is a normal with this distribution. So let's assume that rho is equal to 0.8, so quite heavily correlated. And let's give a starting guess of 0, 0. Okay, the origin. Sorry, the true centroid is the origin, and let's use starting guesses that are at plus minus 2.5. So there's a starting guess at plus 2.5, minus 2.5, plus 2.5, plus 2.5, minus 2.5, plus 2.5, minus 2.5, minus 2.5. So 4 distinct chains. So this is the Gibbs sampler. It is not a complex function. Okay. It has some starting criteria. It has a number of steps, and I've fed it this rho parameter so that we can play with it if we want. We initialize the variables x and y just to be empty, and we give the first value our starting guess. We then loop over the Markov chain. Okay, the Markov chain sets the ith value of x to be a draw from this conditional distribution, one draw from this conditional distribution, given the value of y from the I-1th iteration. Yeah. And the same thing then for y, given the xith iteration, the xith value from here. And you loop this thing, bang, 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 for n iterations. And we can just show the first 15 samples of the Gibbs sequence, and this is what it looks like. So this is the first 15 samples from our Gibbs sequence, starting at starting at our initial guess of minus 2.5, plus 2.5, etc., four starting guesses. And what you can see is that these chains are converging on some blob in the middle, right? And that blob that they're converging on is the target distribution. That's the thing that we want to sample from. If we crank this up to many, many samples, so let's crank it up to, what did I use here? Where is it? I can't see the number anymore. Anyway, anyway, I cranked it up, whatever I cranked it up to, I can't see. But anyway, so we end up with like 10 to the 5 or so samples, and that gives us this distribution here. So you can see I've colored the lines of the different chains in different colors. So you have the green chain in the background, and there's the red, the blue, and the orange. And you can see that they tend to create samples around this, they tend to create values that are clustering around this particular distribution, this skewed distribution. Sorry, this correlated distribution. Because it's now these are samples, it's easier to plot these as just points instead of lines. So we're ignoring the fact that these things go one after the other in a chain, and we end up with something that looks like this. So this is the Gibbs sampler. This is the way in which we generate samples. We can generate samples if we know the conditional distributions that we want to sample from. Okay. If we don't know the conditional distributions that we want to sample from, then we can use a more general method that's referred to, or that's called the Metropolis-Hastings algorithm. And this, again, you might have heard of, but if not, don't worry about it. I'm going to go through it in some detail. Okay. The way in which you construct a Metropolis-Hastings sample is, well, the Metropolis-Hastings algorithm is essentially a form of a general form of the rejection sampler that we spoke about, a few lectures ago, where you had some distribution that, was encompassed by a box, and we then randomly distributed points over the box, and we said, I'll accept those points if they sit below the curve, right? Excuse me. The Metropolis-Hastings algorithm is a mechanism for drawing samples from an approximate distribution that we can sample from easily, and then correcting them so that they end up converging onto the target distribution that we want. Okay? So what this Metropolis-Hastings algorithm does is it sequentially draws candidate observations from a particular distribution, again, conditioned only on the last observation, so it's a Markov chain. And the thing about the Metropolis-Hastings algorithm that is different from what we just spoke about is that the candidate distribution is refined at every single step in the chain. And that means that you get closer and closer to the target distribution with every step. That's how it primarily differs from the rejection sampling, where we had some function, we generated a sample, we checked if we kept it, and we kept it or we threw it out. And then we did exactly the same process n times. The Metropolis-Hastings algorithm differs because it generates things in a way that is refined at each step. So the way in which the algorithm proceeds is we generate some y value from this generation function that we'll talk about, q, which is dependent only on the current state, xt. And we also then draw a random variable from the uniform distribution 0 to 1, just like we did in our rejection sampler. We then define the next step in the chain as the value that we just generated, y. And we then say, if our random variable that we just drew here is less than some acceptance function, which is a function that depends on the current state and the new state, y, then we let the new state become the current state. Then we accept it. Otherwise, we make the next state the current state. So this is what this thing does, this function here, this u is less than alpha of xty, is it says, okay, I've generated a point over there. The probability of the probability density over there is 20%. Do I want to take that as my next sample? I roll a dice, the dice comes up 10%, and I go, yep, I'm going. And I move over there. And what that means is that the Metropolis-Hastings algorithm is able to climb uphill. It's able to go from an area of high probability density to an area of low probability density with some probability. So it doesn't just do the gradient descent thing of falling down the hill into the highest probability area, but it actually explores the probability space. And that's the core, it's the heart of MCMC. Obviously, then we iterate the process. So we're going to talk about this candidate generation function, and we're going to talk about the acceptance probability. The acceptance probability is defined here. So it's defined as the target density, right, at the new location, y, times the candidate generation function, the probability, the density of the generation function at x and y, divided by the target distribution density where we're currently standing, and again, the transfer probability, but now in the opposite direction, x, y. Okay, this is only, and it's obviously 0 if the target distribution has 0 probability at x, right? All right. Sorry, yeah. So if the move is accepted, we move to y, so x gets updated to the new location, xt plus 1 is equal to y. Otherwise, we remain where we are. So there's a few special cases of the Gibbs sampler. Sorry, of the target, the candidate generation function. One of which is the Gibbs sampler that we just spoke about, and that is the Gibbs sampler is a Metropolis-Hastings algorithm when the candidate generation function is the conditional distribution of each variable, okay, like we said. And the acceptance probability is 1 for all sources, because we always accepted a move in the Gibbs sampler. We never had any probabilistic question. There's others like the random walk Metropolis Hastings, which says that the candidate generation function is my random walk function. That is an equal probability of both in both directions or in all directions. And there's another one which is called the independence sampler. The independence sampler is when the candidate generation function is independent of the current location. Okay, so that's another thing. And that gives you a totally different type of Monte Carlo, of Markov chain Monte Carlo. But it's similar to something that we call importance sampling, but I won't go into it. I can happily chat about it if people are interested. An important thing about the acceptance distribution, the acceptance function, is that if the candidate generation function is symmetric, so that is to say that if the candidate generation function has equal probability at f of z as f of minus z, then the acceptance probability, this thing here, q of y and x, is the same as q of x and y by definition. And therefore, the acceptance probability just becomes the ratio of the target distribution density at y, where we want to go, and x, where we are. Okay? So the symmetry of the candidate generation function simplifies the acceptance probability a lot. And there are lots of symmetric generation functions: the Gaussian, the uniform distribution, the student t distribution. All of these things are symmetric around the current location in terms of generating a new variable, and therefore they produce this behavior in the acceptance distribution. Okay, so let's actually do it. Let's spend the last portion of our lecture generating Monte Carlo, generating a Metropolis Hastings simulation of some results. Now, we're going to go over time here. I apologize for that, but there's only a couple of slides left, and this is the really interesting stuff. So hopefully people can stick around. So what we're going to do is we're going to start off by generating a bivariate normal distribution. So our bivariate normal distribution is like we've played with before. It's and the target distribution is trying to figure out what the value of the mean of that distribution is, the mean of the bivariate normal, given some known scatter, which is just an identity matrix. So our bivariate Gaussian is a perfectly independent two-dimensional Gaussian with sigma of 1 in x and y and an unknown mean. Okay, 0, 0. The candidate generation function is going to be also a normal distribution, which has the mean of the location that we're currently at, and has a sigma that is equal to 0.2 sigma, like 0.2 units. So it's smaller than the actual thing that we're trying to find. Okay, what does it look like in practice? Well, this is pretty similar to what we had before with the Gibbs sampler. So we just have the initialization, the starting point. This is defining our row, our covariance, and then we loop over our iterations. Now, the way in which the Metropolis Hastings proceeds is we generate a proposal point. That proposal point is generated from our multivariate normal, and it has it's a Markov chain, so it's based on the previous state. And our generation function had a sigma of 0.2 times the identity, the identity matrix. We then accept that the acceptance function is pi of the target distribution evaluated at the new point divided by the target distribution evaluated at the current point, because our candidate generation function is symmetric. And so that's just the value of the multivariate normal at the current location, at the current location, at the proposed location, prop, divided by the target distribution evaluated at the current location. Okay, we then generate our random value, and we say if our random value is less than the acceptance value, then we accept it. Otherwise, we stay where we are. And that's it. We have the Metropolis-Hastings algorithm coded up, and we can run it. We can then run 10,000 steps of our Metropolis-Hastings with a starting point of minus 10, 10, and then we can plot the chain. And this is what it looks like. That's it. That's our Metropolis-Hastings samples, 1,000 samples from this distribution, and we end up with something like that. What do we do with that now? So there's a couple of important things that we have to, questions that we have to ask in Metropolis-Hastings, in Markov chain Monte Carlo. The first of which is, how do we know that a Markov chain Monte Carlo has been run long enough? How do we know that it's been run long enough and has enough samples? The second is, how do we know that the samples that we have allow us to do unbiased inference? And there's three things, but two primary things that are very important for answering these two questions. The first of which is about this thing here, which is called burn-in. This distribution of samples is very obviously not part of the target distribution, because it's to do with where we started and walking its way towards the main body of the distribution that we're trying to simulate. This thing is called the burn-in, and it is grossly unrepresentative of the distribution that we're trying to sample. And you can actually see this if you plot the value of the parameters as a function of the step number. This thing here is the burn-in, and then these are the samples that we want. And so the first thing that we have to do in a Markov chain Monte Carlo when we have our posterior samples is get rid of the burn-in. Okay, so we pick a point that's well and truly beyond the burn-in. So let's say 200. We throw away every sample before that. So removing every sample from 200 to 0. And we then plot our chain. And this is then our actual posterior samples that we're interested in. The second thing, and this is crucial and often forgotten, not often forgotten, but sometimes forgotten, is that the Markov chain means that sequential samples from the distribution are not independent of one another, because it's a Markov chain, because it's dependent on the current state. And that means if I plot the distribution of the i+1th value of my parameter, and my ith value of my parameter, I get this very, very strong correlation. And the fundamental tenet of our posterior analyses, of our Bayesian statistics, is that the draws that we get in our posterior should be IID observations. They should be independent, identically distributed observations. So this correlation cannot fly, right? And so what we do is we perform something called thinning. And the way in which we get around this, the way in which we do this, is we basically say, okay, there's a correlation, a strong correlation here between the two parameters. What about between the so the first parameter, the ith parameter and the i+1th parameter? What about between the I and the i+5th parameter? So that's this here. There's still some correlation. What about the i+10th? Well, that looks pretty uniform. So that's pretty good. That's pretty even. There doesn't seem to be any strong correlation there. The values of i+10 in theta 2 and i+10 and theta I in variable 2 are independent. This doesn't have any strong correlation. And therefore, I can probably get away with using a thinning that throws away every, that only keeps rather every 10th variable, every 10th sample. Okay. If I could also go to 100 to accept only every 100th sample, but then I'm starting to require a much longer chain in order to get a requisite number of samples. So I'm not really happy with that. So I'm not going to do that. So we can keep every 10th sample, only every 10th sample, and that'll give us something that looks pretty sensible. So last slide. Let's actually apply this to a Bayesian problem. Let's do the whole purpose of us being here. And let's make it an interesting one. So we're going to use our just Metropolis-Hastings algorithm that we just generated, and we're going to answer a real Bayesian problem that we don't know the answer to, and we don't know the situation. So the situation is this. We are given a bag of coins, and we're told that that bag of coins has a certain fraction of coins. There are a certain number of coins in that bag that are biased. We are not told how many coins are biased, nor are we told what their biasing is. We're just given the bag and said, there's some biased coins in there, and they're biased by a certain amount. We draw a random coin from the bag 1,000 times. We toss it 3 times, and we record the number of heads. This is our data. So we drew 1,000 coins, we tossed them 3 times, and we measured the number, we recorded the number of heads. I now want you and me to tell me what the value of the number of biased coins in the bag is and the amount by which they are biased. Okay? And that naively might seem like it's impossible to know, given the data with any sort of accuracy. I mean, there's got to be degeneracies. There's got to be all these sorts of things that could mean that da-da-da. But this is the whole point of Markov chain Monte Carlo. So what we're going to do is we're going to go through our procedure for Bayesian inference. We had these 4 steps. The first step was we need to define a likelihood. Now, our likelihood consists of 3 parts. It consists of the probability of drawing a biased coin from the bag. It requires us to know the probability of a biased coin showing X numbers of heads given 3 trials, because we threw the coin 3 times. And we have to know the probability of a fair coin showing X heads given 3 trials. These are the 3 components of our likelihood. The probabilities of each of these can be described with binomials. Okay, so that shouldn't be surprising. So the biased coin, the probability of a coin, or rather the samples of a biased coin, the results of a biased coin, given some bias, θ1, is a binomial where, oh, that should be 3. It's drawn from n equals 3 and θ1 is equal to θ1, or the biasing is equal to θ1. The probability of observing, I'm sorry, I just completely bottled that. This is the probability of pulling a biased coin from the bag. The probability of observing a biased coin, given the fraction of biased coins that are in the bag, is a binomial where we draw 1 coin. So n is 1, and this is the fraction of coins that are in the bag that are biased, and this is the unknown. The second thing is the probability of a biased coin showing X heads in 3 trials. And that again is a binomial. X heads given a biased coin is this, given a biased coin and some biasing, θ2, is a binomial with n equals 3, the probability of biasing is θ2. And the last thing is the trivial one, which is the probability of X heads in a fair coin is just a binomial with equal probability of heads and tails. 3 trials again. We can therefore construct our likelihood using these probabilities, right? Which is just the probability of observing X heads out of n trials given a fair coin times the fraction of coins in the bag that are fair, plus the probability of observing X heads given a biased coin, times the fraction of coins in the bag that are biased. And this is, again, just a summation of binomials. Theta 1 and theta 2 have to be between 0 and 1, obviously, because they're probabilities. And so we can actually code this up really simply. Our likelihood is just enforcing that theta requirement there. The binomial function with a probability of 50 times 1 minus theta 1, plus the binomial function theta 2 times theta 1. For a totally unknown theta 1, totally unknown theta 2, it could be any value. We then have to define the prior. Step 2 in this process is defining the prior. Determination of the prior. The prior here is easy. We have no idea what the values of the fraction of biased coins is, and we have no idea what the biasing is. So the prior on both thetas is just the uniform distribution between 0 and 1. Okay? So the prior is trivial to calculate. And then finally, we can calculate the posterior distribution. And this is where the sampler comes in. This is where things get fun, things get interesting. So what we do is we generate our Metropolis Hastings using the stuff that we had above, using the prior here and the likelihood here. Now I'm doing this calculation of the posterior in log space rather than in linear space. So I generate a log posterior. And the reason I do that is because if we work in linear space, then the computer rounds things to 0 when they're very, very small. But we don't want it to do that. We want it to be able to distinguish between a part of the parameter space that is likely at 10 to the minus 5 or 10 to the minus 10, and differentiate between that point and a point in the likelihood space that's biased at 10 to the, that's probable at 10 to the minus 7, right? And so to do that, we work in log space. And then we just proceed in exactly the same way we did before. We have some proposal function. Here I've created a proposal function that's a multivariate Gaussian, so I can make this it's symmetric, and so I can make this simplifying definition of the acceptance function. And then I just evaluate my posterior at the proposed value and at the current value. So I calculate the log posterior given the data at the proposed value, and I calculate the log posterior given the data at the current value. And my acceptance function is that my acceptance is still a random uniform draw, and my acceptance is still just this equality here. That is it. With that acceptance function and that proposal function, we have written a Metropolis Hastings Markov chain Monte Carlo. Okay, one of the most powerful tools in modern statistics and empirical sciences. And we can now run it. We can run this given our data and given absolutely no more information than our data and an uninformative prior on the number of biased coins in the bag and the fraction by which they are biased. We can then infer the posterior, the two-dimensional posterior of the bias on the coin and the bias in the number of coins that are in the number of coins that are in the bag. And this is what we get. We get a value for theta 1 that has this burn in here and, you know, falls on some value. We have some theta 2 that again has something here. But we've forgotten 3 things here. The first of which is we've forgotten the burn in, we've forgotten the trimming, and we forgot to start from multiple starting points. So we can do all of that very easily because we've done it all before. The starting from multiple starting points just involves starting it from 10 random starting points. So I've let the random uniform distribution give me 2 points, one in the x-axis, one in the y-axis, and I've done it 8 times, and I've run this in parallel so it runs quickly, and I end up with the total chain that has my samples from my posterior given this random starting point, and it gives me 8 sets. Okay, those 8 sets of random posterior values look like this. okay? Which the different chains here are shown in different colors. I now want to do my burn-in removal. So I'm going to remove this chunk here that's doing something funny right at the beginning here. And I'm going to remove it from both sides. So I'm going to delete the first 200 points. And I now don't have my burn-in anymore. So I'm happy with that. Okay, no burn-in. And now we do our thinning. So again, we try the 5th, the 10th, or the 100th. And it turns out that, yeah, the 10th is probably fine. Maybe the 100th is probably better, but let's just use 10 for funsies. And we end up with our final chain. This is our final chain. These are our final posterior samples. They are samples from the probability distribution. There's clearly something going on with these points. And this is indicating that we weren't probably hard enough with our trimming, and or we didn't run the chain for enough samples for each thing, because in my 8 chains from memory, I only ran these for 10 to the 4 steps. Yeah. And really, that's probably not enough. Probably need to go to 10 to the 5 or something. But we have these posterior samples, and because we have these posterior samples, we can now trivially compute the marginal distribution. The marginal distribution of our 2 values looks like this. It's got a peak at 0.3 and some, 0.05 standard deviation in θ1. And it's got a peak at 0.8 and a standard deviation of, 0.005 again in θ2. And with those 2 distributions, we can now use these PDFs to generate our inference, which is that the value of the number of biased coins in the bag is maximized in my posterior. So the maximum posterior is at about 30%. So 30% of the coins in the bag are biased. And the maximum value of the biasing, or the expected value of the biasing, is 80%. And I can now tell you that the truth that I use to generate these data are 30% and 80%. So the posterior here is giving us excellent inference. We knew nothing about these values other than an uninformative prior. We just had the data, and we had an unknown posterior distribution, and we have then used posterior sampling with Markov chain Monte Carlo and recovered accurate inference. And that is the use and the power of Markov chain Monte Carlo. Oh, great. I'm glad we got through that. I'm sorry we went over. Hopefully that's very useful for you all. If you have questions, of course, as always, feel free to stick on the line and ask them afterwards, but I've kept you here longer than I usually would like to. So please feel free to sign off now. When we start next week, we will be starting with the final section of this course, which is all about doing posterior inference. So we're going to go through and talk about how you do posterior inference, and yeah, we're going to work on that. So it's going to be much more practical uses and much more interesting stuff with regards to actually using the statistics that we've learned throughout the course so far. Yes, thanks very much. I'm sorry that last week's lecture was a bit dry. Unfortunately, when you're talking about prior distributions, there's not really a great deal that you can do to avoid the dryness, but it's a necessary evil, and without that discussion of priors, we wouldn't be able to do the sorts of stuff that we're going to do now, and we did this week, and we're going to do a lot in the next couple of weeks. I'm hopefully going to have a few more of these fun interactive things like we had a few weeks ago in the next couple of lectures. So I've already got some nice plans for that. So yeah, I hope we're going back to the fun interactive part. But this is, I think, really important that we all understand it. Really important that we understand how this works, and that you appreciate the utility of Markov chain Monte Carlo. And it's really going to help us for the fun stuff that's coming in the last few weeks of the lecture course. So thanks very much, everyone, for sticking around. Apologies again for going over, and really looking forward to seeing you all next week when we continue with the real meat of the course, which is all about actual statistical inference. So see you next week.
Bye.